students, as we are seeing important question from solution chapter, today's important question from vapor pressure of a solution of a non-volatile solute and volatile solvent. This is the second category from the Raoult's law. First category, it is liquid solution. Both the solvent and solute are from liquid components, that is also belongs to volatile components. Volatile means what? It is easily evaporatable. Okay, now come to this point. The second category, one it is volatile solvent, the other one it is non-volatile solute. So both the thing we are mixing. Suppose if it soluble in volatile solvent, non-volatile solute will dissolvable in volatile solvent. What will be the result? That will be the question. Okay, now come to this point. If a non-volatile solute and volatile solvent of vapor pressure of a solution, the solvent is what it is? Volatile. Okay. Now, what will be the result? That is a question. So, the result it is the surface of the solution which is occupied by non-volatile solute molecules, so that lesser number of volatile solvent molecules escape into the vapor phase. Okay, now come to this point. Just to watch these two picture. In that first picture, red color dot, it is non-volatile solute. Black color point, which is volatile solvent. So here, volatile solvent which is there on the top, easily evaporatable. But here, non-volatile solute which is going to occupy the surface level of this solution. So naturally it will block that surface. So the volatile solvent which is not easy to evaporate in the vapor phase. That is the answer. Okay, now vapor pressure of a solution at a given temperature is lower than that of the pure solvent. Very clearly they mention the non-volatile solute molecules are blocking the surface. What is inside that? Volatile solvent. So volatile solvent cannot escape easily to that surroundings. That is what they mention very clearly. So the surface of the solution which is occupied by non-volatile solute molecules, so that lesser number of volatile solvent molecules escape into the vapor phase. So this is going to block that, so it cannot easily evaporate outside. Why? Because non-volatile solute molecules are blocking the surface. Okay, now according to Raoult's law, what it has mentioned, P equal to PA is equal to P naught A chi A. What is it P? Vapor pressure. PA, partial vapor pressure of a component A, that means first component. The second, P naught A, vapor pressure of a pure component of A. Okay, now according to this, mole fraction of a component A and B. So, chi A plus chi B equal to 1. Shall we write it chi A equal to 1 minus chi B? Okay, so we can apply this equation where we are going to write it over here. Okay, hope you got an idea how to write. Now, this will lead to that RLVP. Okay, now come to this point. As we mentioned here, P equal to P naught A chi A. Now, chi A plus chi B, that is mole fraction of the component A and B equal to 1. So, chi A equal to 1 minus chi B. Okay, now let us apply this here. P equal to P naught A into 1 minus chi B. Okay, so P equal to P naught A minus P naught A chi B. P naught A minus chi B. Okay, now let us bring this side. P naught A into chi B equal to P naught A minus P. This we are bringing this side. Okay, now let us see that chi B, mole fraction of the component B, equal to P naught A minus P divided by P naught A. So, this is a point we are getting P naught A minus P. We can consider lowering of vapor pressure. Vapor pressure. Okay, now this is only we can say relative lowering vapor pressure. Hope you got an idea how to go for this. Finally, we can come to the conclusion of that non-volatile solute and volatile solvent of the solution can be started as the relative lowering vapor pressure is equal to the mole fraction of the solute. In that also, the solvent should be volatile. I hope you got a better idea about this second category of Raoult's law. Okay, this also they will be asking from the board. How can you prove that vapor pressure of a solution of a non-volatile solute and volatile solvent? That is the way they may ask the question. Hope you got an idea. Okay, now let us go for that ideal solution, non-ideal solution. Why you know? Because from the Raoult's law only we are following ideal solution and a non-ideal solution. You know one thing, ideal gas already you have learnt. The same way, ideal solution which follows Raoult's law, which obeys Raoult's law, that is the ideal solution. Which does not obey the Raoult's law, that is non-ideal solution. Come on, let us go for that ideal and a non-ideal solution. What are the examples of ideal and a non-ideal solution? Very clearly in this session. Now let us go and analyze the important question of ideal solution and non-ideal solution, difference between these two, and where do we get positive deviation, negative deviation, and examples of ideal solution, non-ideal solution. These are all very important question from the board. Yes, come on, let us go for the what do you mean by ideal solution? How do we identify the ideal solution, and what are all the points to be noted in that ideal solution? First and foremost, the solution which obey Raoult's law over the entire concentration is known as ideal solution. Okay, where do we identify for the ideal solution? Delta H mix is equal to 0. That means enthalpy change for the mixing of pure components is 0. The same way volume mix delta V mix is also 0. Okay, now there is no heat evolved or absorbed. That is very important point to be noted. Next, one more important point. Volume of the solution is equal to the volume of the component of the mixture. So, volume of the solution is equal to the volume of the component of the mixture. So, these are all the important points to be noted from the ideal solution. Okay, because choose the correct answer in that any one among will be the correct answer for the ideal solution. Now, non-ideal solution, as we are talking about that ideal solution only, non-ideal solution we will come to know which does not obey the Raoult's law over the entire range of concentration. So that is a non-ideal solution. Okay, how do we identify vapor pressure? It's a very important point to be noted for non-ideal solution. So vapor pressure of a solution either higher or lower than the predicted by Raoult's law. Suppose if it is higher, the solution exhibits, that means it shows a positive deviation. Please note that where do you get that positive deviation? That vapor pressure of a solution is higher, the solution exhibits positive deviation. The same way, vapor pressure of the solution is lower. See, look at that. Vapor pressure of the solution is lower. Then the solution shows negative deviation. So, please note down where do we get positive deviation and negative deviation? We are getting that question from the non-ideal solution only. We are not getting so question from positive deviation, negative deviation from ideal solution. So this is very very important. Where do we identify that positive deviation and negative deviation? That is from the non-ideal solution. How do we identify that positive deviation and negative deviation? Here vapor pressure of the solution is higher than that. That means the solution shows positive deviation. Suppose vapor pressure of the solution is lower, the solution exhibits the negative deviation. Okay, now let us go and check the examples of ideal solution and non-ideal solution, and the main graph about the positive deviation and negative deviation and examples of positive deviation and negative deviation very clearly now. As we are seeing the examples of ideal solution and non-ideal solution, I would like to mention the intermolecular attraction of solvent to solvent and solute solute in ideal solution and non-ideal solution. Generally, here for ideal solution, intermolecular attraction prevailing within the components solvent to solvent, neither solute solute. A belongs to solvent solvent, neither B belongs to solute solute. Molecular interaction are the same order as the intermolecular attraction of the components of the solution solvent solute, that is A and B interaction. See, generally you cannot find perfectly ideal solution, it's very rare. Okay, but still there is a chance of getting that ideal solution. So what are the examples of ideal solution? N-hexane and N-pentane, benzene and toluene, chloroethane and bromoethane. These are all belongs to ideal solution. Generally here ideal solution examples, definitely they may give from the board, that to what it is, choose the correct answer way they will ask the question. Hope you got an idea that molecular interaction of solvent solvent and or solute solute are the same order. See, note the point, same order as the intermolecular attraction of the components of the solution, that is solvent and solute. Both will be the same order only, but it will be vary in non-ideal solution. So let us go and check that non-ideal solution, how the molecular interaction between that non-ideal solution. Now let us see the positive deviation from the non-ideal solution in such a way that is vapor phase of a solution is higher. That means you will get the positive deviation. Vapor phase of a solution which is getting lower, then you will get the negative deviation. As you see in this graph here, vapor phase and mole fraction. As we are seeing here, vapor phase of A, P naught A and P naught B. Here mole fraction of chi A and chi B. As we are seeing in this graph, that up above it is a positive deviation, so the vapor phase of a solution is higher, then we can say it is a positive deviation of non-ideal solution. The same way negative deviation, vapor phase which is decreased, that means it is lower, in such a way we can identify it's a negative deviation. Now let us consider the intermolecular attraction between solvent and solute in the non-ideal solution. Intermolecular attraction between the solvent and solute, that is A and B, molecular interaction it is weaker than those of the solvent and solvent or solute and solute. As we have seen here in ideal solution, that will be same order whether it is a solvent or solute or solvent solvent or solute solute, the molecular interaction will be the same order. Whereas here non-ideal solution, when you are talking about the positive deviation, intermolecular attraction between solvent and solute, that is A and B, molecular interaction are weaker than those of the solvent solvent and the solute solute. That is what here high above, that is higher. The same way here I wanted to mention here, in such a way the solution escaping tendency of molecules from the solution, the vapor phase increase. So vapor phase increases means that is positive deviation. So vapor phase decreases. Naturally, it is a negative deviation. That's what I just mentioned here. In vapor phase of the solution is higher, positive deviation. Vapor phase of the solution is lower, negative deviation. In that same way, intermolecular attraction between solvent to solute interaction is stronger than those of the solvent and solute molecule interaction. In such a way, the escaping tendency of the molecules from the solution vapor phase decrease. Now, where it is weaker, where it is stronger, I hope you got an idea. Intermolecular attraction between solvent and solute molecular interaction is weaker in positive deviation. Intermolecular attraction of solvent and solute, it's stronger. Intermolecular attraction are stronger in negative deviation. Okay, now in that way we can conclude, in such a solution escaping tendency of a molecules from the solution of vapor phase decrease, that is a negative deviation. So these are the main points about what is positive deviation and what is negative deviation, where it is increasing, where it is decreasing, and where which is above high and where which is above lower. You will get a clear idea from this point. These examples are very important for upcoming exams. Please note down here: ethanol, acetone, N-hexane, ethanol, ethanol, water, acetone, carbon disulfide, carbon tetrachloride, and chloroform. These are all the examples belongs to positive deviation. Now let us see one example here: acetone and ethanol. Somehow here bond breaks, that hydrogen bond breaks, so escaping tendency of the components of that solution vapor phase increases. So naturally it is a positive deviation. So bond breaking happens means naturally it is a endothermic process. Please note down, when bond breaks, so that belongs to endothermic process. Endothermic process means you know very well what are the points to be noted. Now, as we are talking about that negative deviation, what are the examples of negative deviation? Chloroform acetone, chloroform diethyl ether, acetone aniline, chloroform and nitric acid, phenol and aniline. So these are all belongs to negative deviation. Please note down and take that screenshot, so that will be helpful for you, because always they will keep that corner of the examples of positive deviation and negative deviation. Choose the correct answer, definitely you will get some or the other way. Okay, now next one, for example here, acetone and chloroform. See, in this way, the bond formation takes place. Hydrogen bond formation takes place. When the bond formation takes place means naturally that is an exothermic process. I hope you got a better idea about the examples and how it is forming, where there is a weaker and where there is a stronger, where there is a higher and where there is a lower. I hope you got a very clear idea about that non-ideal solution of positive deviation and negative deviation. Now, finally, let us see the difference between ideal solution and non-ideal solution, because definitely you may get such kind of question. See, whatever I have given, all those instructions and important points, definitely that will be helpful for your board exam. That is what I'm just giving all those ideas. Hope you got a better idea about this point. Here are the main points to be noted from ideal solution, non-ideal solution. The interaction between the components are similar to those of the pure components, whereas here the interaction between the components are different to those in the pure components. The next point, there is no enthalpy change on mixing, that is delta H mixing is equal to 0, whereas here there is a change the enthalpy change on mixing, that means delta H is not equivalent to 0. The same way, there is no volume change on mixing. Delta V mix is equal to 0. Whereas here there is a volume change on mixing, that means delta V mix is not equivalent to 0. The last point, each component obeys Raoult's law at all temperature and components, whereas here their components does not obey Raoult's law, so that they can show positive deviation and negative deviation. I hope you got a better idea about ideal solution and non-ideal solution. Definitely these may be asking from the board point, so please note down correctly, and if you want you can take that screenshot also. That will be always helpful. In our next class, let us watch azeotropic mixtures, abnormal molecular mass, and the grade point colligative properties. These are all important questions. Let us watch. Yes. Now, thanks for watching, and please subscribe this channel and hit the bell icon so that you will get all the notification. Thanks for watching.